The research investigates the influence of axial asymmetry on the nuclear level density and entropy along the fission pathways of the superheavy nucleus 296 LV. Employing a statistical approach, the authors utilize multidimensional deformation spaces to determine the fission pathways. The analysis reveals a significant impact of triaxiality on entropy, crucial for estimating the survival probability of superheavy nuclei. The paper highlights the challenges in defining entropy precisely in finite quantum mechanical systems like nuclei, which deviate from classical statistical mechanics. The authors focus on the microscopic-macroscopic model, deriving the deformation-dependent level density parameter to estimate the survival probability. A set of master equations is used to obtain the time-dependent fission probabilities and calculate the ratio of decay probabilities for both axial and triaxial paths. This study contributes to a deeper understanding of the statistical behavior and thermodynamic properties of superheavy nuclei, shedding light on the complex interplay between entropy, level density, and fission probabilities. Calculating level densities is a crucial step in understanding nuclear fission, as it involves determining eigenvalues and degeneracy of the nuclear Hamiltonian and counting the number of states within a specific energy interval. Due to the exponential increase in the total number of states with excitation energy, statistical methods are employed to tackle this problem. Sophisticated combinatorial methods have been developed, accounting for factors like parity, angular momentum, pairing correlations, and collective enhancements. Microscopic level densities play a significant role in fission and influence nuclear shape evolution with excitation energy. Relativistic meanfield theory and self-consistent meanfield approaches have been utilized to determine single particle level densities. The level density parameters are calculated using the Yukawa-folded potential, and spin and parity-dependent nuclear level densities are obtained with the moment method. The Fermi-Gas model effectively describes the transition from a paired system to a system of non-interacting fermions as the nuclear system goes from low to higher energies. However, the level density parameter exhibits energy dependence and gradually approaches an asymptotic value as the energy increases beyond the neutron separation energy. Recent findings have demonstrated that the level density parameter strongly depends on the available excitation energy, particularly at low energies. This study combines advanced techniques, including the multidimensional manifold of deformations for fission trajectories, with a statistical approach for computing nuclear level density and entropy. The level density parameter is calculated along fission paths, considering the effects of deformation energy and altered single particle level distributions. The calculations of two extreme cases, axial and non-axial fission pathways for the 296 LV nucleus, are discussed. A two-step methodology is adopted, first constructing a five-dimensional potential energy surface, PES, using the macroscopic-microscopic method and then employing a statistical approach to determine the density of states. The PES allows identifying suitable axial and non-axial fission paths by considering the direction with the most substantial gradient drop in all deformation variables. The method is used to calculate the PES, involving diagonalizing the deformed Woods-Saxon potential to obtain single particle levels. The study considers NP equals 450 lowest proton levels and NN equals 550 lowest neutron levels from the Nmax equals 19 oscillator basis. The construction of the potential energy surface, PES, for nuclear fission is a complex process involving the macroscopic component and the level density parameters. For the macroscopic component, the Yukawa plus exponential model is employed with specified parameters. The deformation-dependent Coulomb and surface energies are integrated using a Gaussian quadrature method. The PES is constructed in a five-dimensional deformation space, including the quadrupole non-axial deformation parameter beta 22. A grid of 29,250 points is used, extended through five-fold interpolation, resulting in an interpolated energy grid of over 50 million points. The level density parameters are calculated based on the superfluid formalism and thermal equilibrium between neutron and proton subsystems. The excitation energies, entropies, and intrinsic level densities are calculated at each temperature, with the critical temperatures for neutrons and protons determined. The research paper delves into the calculation of temperature-dependent microscopic corrections to the energy and entropy of atomic nuclei, a crucial aspect for understanding thermodynamic properties at finite temperatures. Utilizing the backshifted Fermi gas model, the authors fit calculated values of intrinsic level density to obtain the level density parameter as a function of excitation energy. Temperature-dependent pairing corrections are calculated using the BCS model, with pairing energy and entropy corrections derived from discrete and smooth single-particle level distributions. The pairing constant in the BCS equation is adjusted to reproduce the smooth pairing energy at zero temperature. The average entropy is obtained by replacing sums over discrete states with integrals and using the average density of states defined in the paper. Results are presented in the form of potential energy surfaces, PES, projected onto the beta 20, beta 22 plane for the nucleus 296 LV. Two trajectories are selected for in-depth analysis, one encompassing triaxial shapes, marked in red, and another corresponding to axial shape, depicted in blue. The energy landscape is determined by minimizing the energy on a 5-dimensional grid concerning beta 40, beta 60, and beta 80. The inclusion of quadrupole deformations is essential for a comprehensive understanding of the nuclear structure. The non-axial deformation beta 22 significantly modifies the potential energy landscape and reduces the axial barrier by approximately 1 MeV in the nuclear fission process of 296 LV. However, mapping energy in a multidimensional space poses challenges, often resulting in a potential energy surface composed of disconnected patches corresponding to multiple minima in the discarded dimensions. To overcome this, the imaginary water flow technique is employed in the total deformation space to identify the actual saddle point. The potential energy landscape of 296 LV is projected onto the beta 20, beta 22 plane, as shown in Figure 1. Where the dashed line represents the potential fission path from the ground state to the saddle point. The energy scale is measured in MeV and is calculated relative to the macroscopic energy at the spherical shape. Thermodynamic quantities, such as entropy, intrinsic level density, and energy-dependent shell corrections, are computed as functions of excitation energy for each deformation along the selected fission path. The potential energy is calculated using the macroscopic and microscopic components, with the latter being damped with excitation energy. The level density and entropy are calculated at the corresponding excitation energy, taking into account the excitation energy-dependent potential and the change of thermodynamic quantities due to variation of excitation energy. The nuclear system is conceptualized as a microcanonical ensemble isolated from energy exchange with its environment, and the total energy EO remains constant during the evolution of the nuclear shape. The excitation energies under consideration are substantially larger than the alterations in the potential energy surface with deformation, allowing for an approximate thermodynamic methodology to ascertain level densities. The energy-dependent microscopic component of the potential is derived and utilized in equation 23 to determine the excitation energy and the potential energy with damped microscopic corrections. The analysis focuses on the entropy and level density parameters along specific fission paths, which exhibit the most significant gradient drop in all variables and pass through two uniaxial saddle points. The axial splitting path and the non-axial path are depicted in figures 2a and 2b, respectively, showing the macroscopic and microscopic components of the potential energy. The influence of excitation energy on the ground state and the saddle point is evident, as shown in Figure 3, where the ground state represents the lowest energy configuration characterized by a well-defined shell structure, and the saddle point corresponds to a highly deformed configuration where the competition between shell effects and deformation energy is crucial. The variation of potential energy, macroscopic energy, and microscopic correction at zero excitation energy is studied as a function of the deformation parameter beta 2 for axial and triaxial paths of 296 LV fission. This highlights the destructive nature of excitation energy on the entire fission barrier, which diminishes with increasing excitation energy. The fission barriers are then presented for both axial and triaxial fission paths, emphasizing the damping effects on the fission barrier. Additionally, the variation of the level density parameter with deformation along the fission path is explored, which is significant for nuclear survival probability calculations. Figure 4 illustrates the variation of fission barriers with excitation energy U0, showcasing the impact of potential energy surface, PES, on fission pathways. The figure demonstrates that PES has a more significant influence on the fission barriers at lower energies than anticipated, with a notable difference between axial and triaxial fission paths. The authors highlight that the damping of microscopic correction systematically affects both fission pathways, although the effect may seem small. However, this damping significantly impacts the ratio of level density parameters AF and N, as it affects the ground state, GS, and saddle point, SP, differently. At small u0, the value of a SP is comparable or even smaller than a GS, consistent with previous findings that the ratio AF and exhibits an increasing trend with excitation energy. Figures 5 and 6 present the level density parameters calculated with and without damping along axial and triaxial fission paths at U0 equals 15 and 35 MeV, highlighting the significant impact of damping near the ground state. Figure 7 illustrates the variations in entropy along the axial and non-axial fission paths at energies U0 equals 15 and 35 MeV, demonstrating that the entropy systematically decreases when potential damping is included, regardless of the chosen path. The impact of microscopic corrections on the entropy of nuclei during the fission process is analyzed, focusing on their influence on level density parameters and entropy values along axial and triaxial fission paths. Excitation energy and deformation effects on entropy are examined, revealing the crucial role of damping in microscopic corrections. Notably, damping significantly alters the entropy behavior as a function of deformation. At low excitation energies, entropy is maximized at the ground state due to the dominant role of excitation energy. However, as excitation energy increases, the entropy curve trend becomes less pronounced due to the growing influence of the density of single particle states. Damping reduces the excitation energy's impact on entropy, while the density of single particle states remains unaffected, leading to a smearing of entropy as a function of deformation, regardless of triaxiality. The difference between entropies at axial and triaxial saddle points decreases with damping. Calculations with fixed excitation energy along the fission path reveal that the entropy curve trend resembles the potential energy shape, with the structure effect gradually decreasing with excitation energy. Entropy is generally higher at saddle points than at the ground state due to the increased complexity and disorder of deformed configurations. The damping effect is more pronounced at the ground state than at larger deformations, resulting in enhanced entropy ratios at the saddle points. Research into the impact of entropy on decay properties reveals that fission probabilities vary significantly for axial and triaxial paths. To calculate decay rates, a simplified approach is employed, discretizing trajectories into grid points. Master equations are used to determine the probability of the nuclear system being populated at each deformation, taking into account transition rates and level densities. Analysis shows that at lower energies, the triaxial path dominates, whereas at higher energies, both paths become comparable. The ratios of fission probabilities, including the effects of damping, are presented in Figure 9. Notably, the competition between paths should be accounted for at all intermediate points, particularly when considering damping effects, to accurately model the fission process. This study highlights the importance of considering the interplay between axial and triaxial paths in understanding decay properties, emphasizing the need for a comprehensive approach that incorporates the effects of entropy and damping. By acknowledging the energy-dependent dominance of triaxial paths, researchers can refine their models to better capture the complexities of nuclear fission. The authors delve into the fission process, emphasizing the role of entropy and its fluctuations along the fission paths. Figure 9 illustrates the ratio of fission probability through the saddle point, SP, of axial fission path to that of triaxial fission path as a function of excitation energy, with and without damping of microscopic corrections in potential. The results indicate that the axial path, which has an SP closer to the ground state, achieves a non-zero decay probability more rapidly than the triaxial path when damping is considered. The decay constants, lambda, are determined by fitting the NSP, T, with the equation NSP, T, equals NSP, infinity, 1 e caret, lambda T. The ratio lambda tri, lambda ax of decay constants corresponding to the triaxial and axial pathways is presented in Figure 10. With damping, the axial path reaches its asymptotic probability ns pax, infinity, faster than the triaxial path. And this effect increases with excitation energy. The authors acknowledge that collective effects have not been incorporated into their analysis, which primarily focuses on examining intrinsic level densities along fission pathways under the assumption of a gradual and slow motion in collective degrees of freedom. However, they note that the qualitative trends observed in their results as a function of excitation energy remain consistent, even when collective effects are included. This study underscores the importance of considering both the shape of the potential energy surface and the entropy, which incorporates both energy and structural effects, in the study of fission. The findings demonstrate that variations in structural effects at different points of the fission path can lead to significant changes of the level density and, correspondingly, of the entropy, especially in the case of axial symmetry. The study investigates the role of entropy in the fission pathways of atomic nuclei, employing the master equation to compute time-dependent decay probabilities. It highlights how the behavior of entropy along fission paths influences fission probabilities, with comparable decay constants for axial and triaxial paths indicating minimal path dependence. The paper discusses various theoretical models and experimental findings, emphasizing the importance of considering entropy in fission calculations and suggesting avenues for further research to enhance understanding of the fission process, including the need to expand the study to encompass additional degrees of freedom.